Yes, I really totally.
Remy, can you check that on Zoom you see this without any other windows?
Why is it covered?
Oh, that's what I started shaking.
Oh, is it?
Going forward, yeah. I realized that was something. Yeah.
Oh, it's early. This is why nobody's here. You're not.
That's something that my first try. I thought, oh, I can do this myself. So I interviewed at the first. I had a message. So getting the position where you're just standing up.
Yeah. Oh, it's getting crazy.
Any other template?
No.
Sorry. Also in French and French.
French.
Yeah. Yeah.
Like, which one is yours? Like I said Japanese. Every single day, like learn new stuff every week. It's like so much like memorization. Yeah,
I feel that I need to put in more time to get more out of it.
I think so. But if you ever go to France, now you'll have like elementary French skills.
Yeah.
out there.
I don't somewhat understand what you said. Yeah, yeah. I don't know.
Yeah, I'm working on. Very good.
Yeah, here's the beauty.
Yeah, I work for places
Okay.
like crypto and.
Oh, it's so
Well,
yeah,
but
yeah.
it's always fun to just,
Yeah.
Okay, so it's 11:10, so I think it's time to start, and people will come. I think people will still continue to come. So I want to start by saying what I said yesterday in the email. Thank you for putting so much effort into the homework. I really appreciate this, and some of the LaTeX formatting, they are just beautiful. Some people use an iPad and write by hand, and this is fine too. As long as you put effort into understanding the question and understanding the proof and finding the proof, this is a time very well spent. So yeah, I really appreciate this. And the next homework is already out. So this is an excuse for me to tell you that, yep, you need to worry about the next homework. So the plan now, the original plan was to start database constraints today. But I decided that we don't want to rush over these generalized bounds, which we actually didn't even cover last time. So some of you were brave enough to solve problems 2C and 2D, although we actually did not discuss the generalized bounds in class. So I want to recap everything that we did in the previous lectures, kind of open your intuition about what else is out there, and also prepare you for the current homework, which is related to, it's about these generalized bounds. And on Thursday, we will finally start database constraints. And thinking about it, actually, there are lots of topics that I actually knew very well, but I forgot about them. that connect classical database constraints, functional dependencies, multivariate dependencies, to something used way back in AI, which are the implication problem for conditional independencies. And it connects, the modern connection is to entropic functions. It's a beautiful connection. So all the effort we spend on understanding entropic functions will pay off on Thursday and probably next week when we continue this discussion. Okay, so recap of the AGM bound. This is going to be relatively quickly. These are the definitions of a fractional edge cover and a fractional edge packing. The edge cover asks that for every vertex, the sum of the weights of all the edges that contain that vertex be greater than 1. The vertex packing assigns weights to the vertices, and for each edge, the sum of the weights of the vertices for that edge needs to be less than or equal to 1. And the goal in the cover, we want to minimize. We want to have a small cover. The goal in the packing is to maximize. These are the two linear programs that define these two optimization problems, and they are duals to each other. There is a systematic way in which you look at one of them and to construct the other one, the dual. And you should know how the systematic way goes. Every constraint in one program becomes a variable in the other program. Every variable in the first program becomes a constraint in the other program. The optimization function on one side becomes the constraint on the other side, and vice versa. This is how you go from one to the other. A quick check that you did the primal dual translation correctly is to check the weak duality property. The weak duality says that for any feasible solution here, we want it to be small, but the property holds for any such feasible solution, the value here is greater than or equal to the value of any feasible solution from here. The proof is amazingly simple, something you should internalize and check. Here is how it goes. So let me go back. We start from this value, the sum of all the weights of the fractional edge packing. And then we observe that 1 is greater than the sum of the vertex covers for that particular edge. So I just expanded here with this expression for the edge E. Okay? Yes, Joe.
Clarification, the parenthetical there is an explanation or you multiply? What? The thing in parentheses, are you multiplying by that or is that a definition?
I'm multiplying.
You are multiplying, okay, sorry. Yeah.
And they come from 1 greater than this sum, which is this thing here. Okay, so now what we do, obviously we have two sums, we switch them. Instead of summing over the edges and then summing inside for each node in that edge, we sum over all the nodes. And then inside we sum over all the edges that contain that node. Okay, and now, since we have grouped by the sum of the weights of the edges, we apply this inequality. Look how beautifully. So no matter what feasible solution we have here, its value is always greater than the value of any feasible solution from here. So we want to minimize the one on the right. We want to maximize the one on the left, but they can't exceed each other. And the strong duality property, which requires a deeper proof, says that they can be made equal. This is a general statement for all primal dual programs. In the case of the fractional edge cover or the fractional vertex packing, this optimal is denoted by a rho star, and is called the fractional edge covering number. Okay, yes.
That should be a max, right?
Yes. I expect there will be many mistakes on these slides. So yeah, but also it's a way for me to check that you're awake. Great. So this is number 1. So the AGM bound in its original formulation, and it's in its simplest instantiation, assumes that all relation sizes have the same, all relation sizes are equal. They are n. Actually, it should be less than or equal to n. Then the AGM bound is really the fractional edge covering number. What it says is that for any input database, the size of the query is less than n to the power of this rho star. The proof of the bound uses entropic inequalities, and we will recap this soon. But it's not the only proof. You can also completely avoid talking about entropic functions and prove this in an elementary fashion. I'm not going to show this in class, but you know, I worked this out, and it's a beautiful argument. The dual gives you a lower bound. So we use a dual in order to construct this product database by using an optimal fractional vertex packing. And then the size of we still need to round here. I didn't include this in the formula, but n to this I star is not necessarily an integer. So when we round, we might have an error which is as bad as factor of 2. Yeah, we need to round down, and then we can this can be half of the non-integer number here of the real number. So what this product database gives us is a database where all the relation sizes are less than or equal to n, and you can inflate them to make them n, but we don't need to do this. So they are less than or equal to n, and the size of the query is almost n to is almost the AGM bound up to this factor 1 by the 2 to the number of variables. Okay, this is the beauty of the AGM bound stated in this way when all the relation sizes are equal. So quick recap. Here is a query. It is a chain of length 5 from 1 to 2, from 2 to 3, from 3 to 4, 4 to 5. What is an optimal fraction? What is an optimal fractional edge cover? How should we cover these A1, A2, A3, A4 in an optimal way? What would you put here? You've done the homework, so you know a lot. What do you put here? I don't know. Some of you struggled. Some of you actually wrote the entire LP program, and I mean, I shouldn't say struggle, but took it the hard way. I prefer the shortcut. So when I see it, I just write down the fractional edge cover. What is it?
0, 1, 0.
0, 0, 1, 0, 1. That's no good. Why not? Because we need to cover x1. So x1 only occurs here. We need to put a 1 here. And we need to put a 1 in x5. And then the rest is kind of natural. You still need to cover x3 somehow. And here you have a choice, 1, 0, or 0, 1. How do we know this is optimal? You know it's optimal if you find the dual. If you also guess the dual fractional vertex packing. And how do you pack? Well, now I want to make it big. So I'm going to pack, I'm going to put 1 on x1, 0, 1, 0, and 1. And they have the same value, 3. Okay. Any questions about this example? Yes.
Vertex packing and putting values on x1 and x2 such that no edge is greater than 1. I want to maximize. Okay, cool.
Yeah. You could put 0 everywhere, but then it's not maximum. Okay, next one. This is a cycle of length 5 from x1 to 2, 3, 4, 5, and then back to 1. How do you cover this optimally? Half on every edge. And what is rho star in that case? What if you put half on each of them? There are 5 by 2. This is rho star. And indeed, there is a matching fractional vertex packing, which is also 1/2 everywhere. Okay, one more, 2 more. What about K5, where we have 5 variables, and for every pair of variables, there is one atom that connects them. The graph is fully connected, the complete graph with 5 nodes. Gee, what is rho star here? Yes?
Can you just use one, put one on one? Oh, maybe not.
The one,
That's the
no,
one.
yeah, I was thinking maybe it's just 1/2, or maybe it's 2.5.
Quarter everywhere.
1/4 everywhere. Very good. Why 1/4?
So we have 5 times 4, 20. So we cover everything 4 times. So you can do quarter and you do that on 2.
It's perfect. Yeah, I agree. This is a reasonable. I would describe it equivalently by saying that if you look at each node, like node number 1, it occurs in 4 different edges because there are 4 other. So if you put 1 4 on each of them, then you have covered node number 1. And to check it's optimal, actually it's easier to find the fractional edge packing. If you put 1/2 everywhere, you can't do any better.
Can I put 1/2 on all the edge on the cycle though? Because in a K5, there's also the cycle.
Yep, you can also do this. You can choose a cycle in K5, put 1/2 as we did above, and the other 0. It's also 1. The next question is, what are the vertices of the fractional edge covering polytope? And I actually don't know. Is a cycle a vertex or is this a vertex? Okay, and the last thing I wanted to show is not just graphs, it's also hypergraphs. Here is a hypergraph that is complete. So there are 5 variables, x1 to x5, and we have 1 atom for each subset of 4. So what is here? How much do you need to cover? Let's cover. It's easier to compute a fractional edge cover here than a fractional edge packing. So in order to cover x1,
You do 1/5.
1 by
1/5.
1/5 is not enough yet.
Harder.
1
Harder again.
1/4 exactly. And why 1/4?
You have to 4 in each, and then you have 5 of them.
Very good, because x1 occurs in 4 atoms. So in order to cover it, we need to have 1/4. So I didn't write that, but it's 1/4.
Why is it 4? 3 choose 4 choose 3.
There's 5 total, but it's missing 1.
Oh, 5. Okay, 5 choose 3. Okay.
Yeah, there are only 5 hyperedges here. This actually has an interesting consequence through Miss-Whitney. If you increase the dimensionality from 5 to 6 to 7 to n, then the rho star actually decreases, which is bizarre. It means that although the query becomes more and more complicated, it's actually cheaper to compute. And this has applications when you have a very, very wide table and you want to check in this database instance if there is any functional dependency. Then what you need to do, you need to compute this through Miss-Whitney and check if you have any extra tuples. If you don't have any extra tuples, this means you have a functional dependency somewhere there. And this can be done very efficiently, almost linear in the size of the database. Very interesting consequence. We'll talk about this next time or next week. Okay, good. So that was the AGM bound in its classical setting, where all cardinalities are equal. The same theory is equally elegant when we extend it to arbitrary cardinalities. So then the AGM bound is no longer this n to the rho star, but it's a function that depends on all these cardinalities. And we don't stop at a single fractional edge cover, but we need to consider multiple. All the vertices of the edge covering polytope. And then the AGM bound is a minimum of over all those fractional edge covering numbers. But how do we find it? It's when we write on pen and paper, yeah, we can have a good feeling about what these fractional edge covers should be, and we can write down this formula, this mean. But in the system, this is not the way to proceed. Instead, in a system, what we want to do is to represent the AGM bound using, again, a linear optimization problem. Pretty much similarly to the one that we used to define the fractional edge cover and fractional vertex packing. Okay, so here is how that looks like. So it's a little bit a lot to swallow, but it's exact, almost identical to the previous slide that you saw. We have the same query, a conjunction of atoms. There are M relations and variables. And now what we need to minimize is the sum of the WJs times the logarithm of the relation sizes. And they are no longer all equal, so we cannot ignore this factor. But the constraints remain the same. The W's continue to be a fractional edge cover. How did we get here? This is what we covered last time, but this is the conclusion of the derivation of the AGM bound. Dually, the dual program now talks about something that looks like a fractional vertex packing, but the coefficients that we had here as the objective function now become the coefficients of the constraints. So it's technically no longer a fractional vertex packing that we're looking for, but something that looks quite similar. And the statement is that for the primal, we use those entropic arguments to prove that the size of the query is always bounded by this formula, that's the AGM bound, the products of the cardinalities to the power of the WJs, and this holds for any feasible solution. We want to minimize it. And for the lower bound, we take any feasible solution of the dual, and we convert it into a product database, and then we get the same slack factor 1/2 to the n, but we still get an almost matching lower bound. Weak duality still holds. This objective value is always greater than or equal to this objective value. But now keep in mind that the VIs are no longer 0, 1s. They can be much bigger. So there is a log of R included here. And by strong duality, quick check, if people are awake. This should be max. This should be this should be max. Okay, these are the two dual linear programs, and we will come back to them. So it's good to internalize them. Okay, so wrap up. So the AGM bound is tight up to a factor that depends on the number of variables, but it's probably much better in practice. Because in order to get that error of 2, you really need to have very small cardinalities. So I guess in practice, it's much better. The original paper, interestingly, it's a theory paper. It's a pretty deep one, actually, beyond the AGM bound. So Alterias, Grohe, and Marx, they tried to see if you can improve over this. And they found a very complicated query with n variables, where n is very big, where this is unavoidable. You cannot remove this factor. And they state in the paper that unfortunately their bound is not tight. They tried hard to remove this factor, but today we accept that factor and we think about the number of variables as being constant. So we don't worry about it so much. We say it's tight. Just a nice story. Yes.
Sorry, where does this factor come from?
This factor comes from the fact that when you compute the product database, you need to take either n to the power vi star or 2 to the power vi, depending on what you put here. And that is not always an integer. I would say this is almost never an integer. So then you need to round down. You cannot round up. Why can't you round up? What happens if I round up? Then you violate the cardinality constraints, and we don't want this to happen. So we need to round down. And the question is, how much do we lose if we round down? Well, each variable can be at most half of what we would like it to be. At least half of what we like it to be. So each variable contributes a factor of 1 to.
But then n isn't the number of like total variables, it's the number of variables in a particular atom, right? Because at most, is that true?
It's true.
Okay.
No, sorry, it's not true. That is n for the cardinality of one relation Rj. But what we care about is the size of the query answer. And the query answer contains all the variables.
But isn't the integrality gap actually proportional to like 1 over the product of like the VI minus 1s or something like that? You know, like the 1/2 is things like only happens if like the VIs are like 2.
Yeah,
So
it's very
Maybe like 1 over like VI minus 1 of VI, product of that, right?
Unfortunately, with the way it's written here, we can't really argue about this. But yeah, you get n to the power VI for each variable, and this is what you need to round down. So how bad can it be? Well, if I have 1,000,000.05, then I'm losing very little. But if the AGM bound tells me I need to construct a variable with 1.99 values, from 1.99 I need to decrease to 1, and then it's almost half. So Grace, I think your point is that for databases, we expect these numbers to be big. And then we shouldn't worry about the factor 1. True and not quite. Remember that sometimes VI is 0. Yeah, we had many cases where VI was 0 right here. Yeah, so then here we get 1. So who knows if the cardinalities are all over the place? I don't have a good intuition of how big those VI stars can be, and whether we should expect these numbers to be big and 1 only occasionally. I don't know how to think about it. So to be safe, we cannot prove anything better than 1/2 to the number of variables here. We have a worst case database on which the query output size is at least 1/2 to the n times the AGM bound. And this 1/2 to the n, they proved in that paper, cannot be improved. Cannot be improved in a fundamental way, in a way that works for all n, for very, very wide queries. Okay, so the AGM bound is really elegant, and it is tight according to this discussion, but it only uses cardinalities. However, there is a beautiful extension to simple functional dependencies. This doesn't have a good history in the literature. The idea of replacing the variables with variables plus, this is something that Dan Olteanu and Christoph Koch described in a paper on probabilistic databases. They didn't give it a name, but it's such a cute idea. We used it in a paper to make it, to apply this to the AGM bound. Although I'm pretty sure this was for Cloro already. And I think we called it query expansion. I usually want to give a name to cool ideas, and we called it query expansion, but the credit should go to that forgotten paper by Dan Olteanu and Christoph Koch. So far, we did not discuss entropies. You do not need to worry about entropies if the AGM bound is all you care about. However, if we want to extend beyond cardinalities, then yes, we do need to care about entropies, and they will play a critical and a beautiful, I would say, role. And the last comment I want to make, which is important, the AGM bound is computable in polynomial time in the size of the query. You just solve that linear program. And if your query has, I don't know, 1,000 joins, then you can still compute the AGM bound quite efficiently using the linear program. Probably you don't want to use the AGM bound for a query with 1,000 joins. But as you will see, this is no longer the case when you extend to arbitrary statistics. Cool. So let's move to general statistics. And before that, I want to do a recap of the theory of entropic functions and entropic vectors. It's a beautiful topic that is, yeah, it turns out to be so fundamental in several areas in databases, and this is an observation that only recently became clear. So the motivation is that we want to extend the AGM bound to more statistics. And again, you already did this on the homework, some of you, but I will go slowly over this extension today. And moreover, it turns out we can also use entropic functions to reason about constraints, about functional dependencies, multivariate dependencies, the implication problem for conditional independencies in graphical models. Very interesting. And as I will argue, they actually lead to a much more elegant treatment of those implication problems than the original approaches. Okay, so let's talk about entropic vectors. Here is a quick definition from last time. The entropy of a random variable is this formula, sum of probability times log of probability over all the probabilities of all the possible outcomes of the random variable. Yeah, everybody remembers this. Good. Usually in our setting, so in machine learning, this is used in a completely different way. They talk about the KL divergence, they use certain properties of the entropy. We go a different route. We consider n random variables and joint random variables, and then we examine the entropy of any subset of these random variables. And we think about the entropy as a vector. I often call it an entropy function, and I think of it as a function that takes a subset of the variables and gives me the entropy of that subset of variables. Yep, it's a vector. From the entropic vector, there are some derived quantities. And this is something I didn't quite cover last time, but they are simple and super important. One is called the conditional entropy. The conditional entropy of V conditioned on U. In this class, we will take it as a definition. This is the entropy of UV together. This is the union of these random variables U and V minus the entropy of U. Yeah, take it as a definition. At least one of you looked it up on Wikipedia because you didn't know what it is. It was on the homework. Thank you. And yeah, you got it right. This is what it is. It's a difference of these. If you turn it around, this is called the chain rule. It's the same thing. It just says that the entropy of U plus the entropy of, oh boy, what's wrong here? What should it be? We need to get that. What should I fix here? How should this look like? V given U, the entropy of V. It's the same thing as here. So their sum is equal to the entropy of UV. Yes?
Why is it called the chain rule?
No,
It has nothing to do with the chain rule and that, like, happiness.
yeah, that,
Probably, right?
I don't know which channel you're thinking about,
Okay, cool.
but it's yeah, it's what you see is what you get. Is that there is also a chain rule for the mutual information actually. The other, the second and last information quantity that I didn't define last time. We won't make much use of it today, but it's important to know. It's called the conditional mutual information. This takes three sets of variables. Usually they are disjoint, but they don't need to be disjoint. Imagine that they are disjoint. So U, V, and W. And the conditional mutual information of V and W conditioned on U is this expression. So the entropy of UV plus the entropy of UW minus the entropy of force free minus the entropy of just U. And you should recognize this expression. It's an expression that we encountered last time and also in the homework. What is this expression here? In the context of an inequality. This is exactly the expression that we say is greater than or equal to 0 to state the submodularity inequality. And this is what the mutual information is. It is a measure of that submodularity inequality, how much does it deviate from 0? This is how to think about it. It's called conditional mutual information. I should also mention this difference also corresponds to a Shannon inequality. To which Shannon inequality? Well, there is only one left. So we had some modularity, and the other one was monotonicity. The conditional mutual information is greater than or equal to 0. It's the monotonicity statement. Yeah, and I have this summarized on the next. No, I don't have the next slide. Before that, I want you to tell me I want you to tell me the entropic values and all these metrics on for the entropic vector associated to this probability distribution. This is a very interesting probability distribution. I hope we will have time next lecture or the, next week to come back to it. It's super important. 3 variables, 4 possible outcomes. All outcomes have probability 1/4. This probability distribution defines, as we discussed, defines an entropic vector with 8 components, which I started to draw here. The entropy of the empty set is 0. I give this away. My question to you is, what is the entropy of all 3 variables, x, y, z? One thing to remember is that the entropy of any random variable is less than or equal to log n, log of the size of the domain. In our case, what is n? What is the size of the outcomes of x, y, and z? How many outcomes do they have? Yes, do you know? Sorry? You're thinking about a single variable, but I'm thinking about the joint random variable x, y, z together. Sorry? 4 outcomes. So the entropy cannot be bigger than log 4. But we have a second rule that if the distribution is uniform, then the entropy is equal to log n. So what is the entropy here at the top? Log 4, which is 2. Beautiful. Okay. What about the entropy of x? Log 2, which is 1. I forgot it's log n base 2. The entropy is always log n base 2. Yeah, so this is 1. Everybody cool with 1? There are 2 outcomes, 0 and 1. 0 has probability 1/2. We need to add them up. 1 has probability 1/2. We need to add them up. So it's uniform, 2 outcomes, entropy is log 2. What about the next one, HXY? What is the entropy here? It's 2, beautiful, because it has 4 outcomes as XYZ, yeah? Good, and the others are the same. This is how you think about an entropic vector. Okay, now let's check a condition. What did I write here? No, I don't know what this is. I think I know what it is. I forgot to put the conditional. I want the conditional entropy of y given z. There is a bar here that is missing. What is the conditional entropy of y given z? I put here the definitions. And I showed here where you look them up. This is the entropy of yz minus the entropy of z. It's 1. Very good. Except that there is a horrible type here. This should be conditional. Intuitively, what this says is that if you know z, then the remaining entropy of y is no longer 2, but it's just 1. It decreases to 1. Okay, here I got it right. What is the entropy of y conditioned on not just z, but then on yz? And you can look them up here. So what is this? Sorry?
0.
It's 0. Very good. It's 0. When you condition on more, and I hate that I forgot the bar here, but when you condition not just on z, but on yz, the conditional entropy can only decrease. As you move from this difference higher up to this difference, that difference can only decrease. Another way to think about this is that since this is 0, it means that once you know xz, then y is uniquely determined. There is no more randomness left in y. And now if you put your database hat and look at this table, you observe that xz is indeed a key, right? Once you know x and z, you immediately know y. Actually, each of them is a key. Yes, Remy.
So is the conditional entropy related to some kind of notion of the average entropy of the conditional distribution?
Yeah, next slide. I'll get to there. I get there. Yeah, right now it's just mechanics of applying these formulas, plus my hints about the intuitions, what these formulas tell us. But I will make this precise on the next slide. Okay, last check the conditional mutual information. What is, and now you look at a diamond. You see, we take xy, xy at the top, and their intersection at the bottom. What is this conditional mutual information? You have the formula here. You put a plus here and a minus here, you add them up. This is 0. Yep, it's 0. When it's 0, that means that those two random variables are independent. And indeed, if you look at x and y, they're independent. The probability of x and y together is 1/4. It's a product of the probability of x being 0 and y being 1. What if we condition on more? What if I condition here on not on the empty set, but I condition on z? That's the only thing that's left. Will the conditional mutual information always decrease? Let's see this. What is the conditional mutual information of x, y conditioned on z? It's right here.
1.
This is 1. This is where the trouble starts with entropic vectors. This doesn't decrease. It may increase. And this distribution is the simplest one for which this phenomenon happens.
So should I interpret this as like the correlation, condition on z, the correlation of x, y increases?
Yep.
Okay.
This is I mean, it's such a beautiful example. It occurs often in graphical models. There was a blog post by Judea Pearl on causality, arguing about whether you should use all your covariates when you compute the causal effect. So you want to see if, I don't know, if drinking water increases your health, then you condition on all the other covariates that you know in order to compute the conditional probability of being healthy when you drink water. And he said, no, you should not always condition on all of them. Imagine the following experiment. We take two random variables, x and y, we flip them randomly. Is there a causal effect from x to y? These are two coins. They are completely independent. Okay, where is my pointer? Yeah, so x and y are completely independent. There should be no causal relationship. But now I introduce a third variable. Somebody raises a flag when these two outcomes are both odd or both even, and lowers a flag when they are opposite parity. This is z. And now if you condition on z, suddenly x and y become correlated. And suddenly you discover a causal effect between x and y where there is none. It's a beautiful experiment. Two random coins. If somebody observes them and raises a flag or lowers a flag, depending on their outcomes, you have suddenly introduced a correlation. If you condition on that flag, you have a correlation between these two random variables. Cool. So we are back to entropies. And as Remy asked, I try to convince you that we never need to use the original formula. We can forget about this and only use those algebraic properties. But at some point, we need to make the connection between the mathematical definition of entropy, which is this formula. It's a stroke of genius, if you ask me, not just me. So the entropy is really a fantastic concept. This is the formula that defines it. So we need to establish that this formula indeed implies those algebraic properties that we want to use in exclusivity without getting back to this formula. This is on the homework. Yes. What? Yes, minus. Thank you. You are awake. So error number is 3. So I have lots of things to fix. So you need to prove that the entropy is between 0 and log n. You need to prove that it increases. You need to prove that the sum modularity holds, or equivalently that the conditional mutual information is always positive. And this is what Remy asked for. What is the conditional entropy? It turns out that the conditional entropy has a following interpretation. You consider conditioning, really conditioning the probability space on a fixed outcome of the variable u. This gives you a standard probability space. It's just restricted, it's conditioned on one particular outcome. Compute its entropy, and now take the expected value of this entropy over all possible values of u. That is the conditional entropy. Okay, it's not obvious, so don't try to derive it right now. But if we spend in paper, it's not that hard to prove. By the way, I claim that from here, if you prove what is above, it should be immediately obvious that the conditional entropy is greater than or equal to 0. Why is the conditional entropy greater than or equal to 0? Well, we need to check that this is greater than or equal to 0. But this is just a standard entropy, which is, if we prove item number 1 is going to be greater than or equal to 0. It's actually trivially greater than 0, because if I put that minus sign here, and the PIs are less than 1, then it's greater than 0. Okay, so this is part of the homework. And the last thing to check is that the mutual information is 0 if and only if there exists a conditional independence between the variables v and w conditioned on u. Once you have this, then indeed you can forget the formula and only use these algebraic properties. Good, cool. So now let's use them for databases. And here I just need to remind you how, no, sorry. This is a slide where I want you to build a deeper intuition about how entropic vectors help us think about cardinalities of databases. So think about the entropy of a pair of attributes as being the log of the cardinality of that projection. So if I say that the entropy of x is less than the entropy of xy, less than the entropy of xyz, what does it say to a database person about a table with xyz? This is an informal statement. And I would claim that this tells me that the cardinality of the projection on x is less than or equal to the cardinality of the projection xy, less than or equal to the cardinality of the entire relation, which has variables xyz. Yeah, this is one way to think about the entropy. What does it say? The entropy of xy plus the entropy of z greater than or equal to the entropy of xyz. think that the entropy is log of the cardinality of the projection.
Join,
Yeah, the joint.
join is going to be larger than, I don't know, something.
Yeah, then the size of the relation. This is what it tells us. We don't even have to join. The cardinality of the projection on xy times the cardinality of the projection on z is greater than or equal than the cardinality of R. Kind of obvious. Right? You project them and then you multiply back and you get everything and plus extra stuff. But okay, one more. What happens if I condition on more? So if I condition just on x, what is the interpretation of this? How do you think about conditioning the entropy of yz condition on x, which is the same as saying the entropy of x, yz condition on x? How should we think about this? When you condition on x, it means that you condition, sorry, I should point here, you condition on each of the individual values. So the condition on A gives us an entropy of probability space with 3 outcomes. Conditioning on B gives us 2 outcomes. So this has related to the number of the degree of the values entries in X. And the second one is related to the degree of pairs XY. So this is what it tells us. It's the actually tells us that the maximum frequency of X is greater than the maximum frequency of XY, something like this. These are kind of informal reasonings, and they sometimes fail, so we have to be careful. So for example, if I take submodularity, and I try to write down the corresponding statement about cardinalities, I need to write as a projection on xz times the projection on yz is greater than the size of R times the projection on z. And this fails. The xz, they have am again, and an. So this is 2, then bm. This has 3. So projection on xz has 3. Projection on yz, xm, ym, and xn, also 3. R has 5 tuples, and z only has 2. So we get inequality in the opposite direction. We can use entropies to derive very powerful inequalities, but we need to be careful. We need to be rigorous about what probability space we assume and how do we get to that inequality. The problem here is that we can only equate the entropy to log of the cardinality if the distribution is uniform. So we can choose one uniform distribution, and then one of these entropies will be equal to a cardinality, but then the others are less than or equal. And here we have 2 on both sides, so there is no good choice of how to define that distribution. Yes, Remy?
So can you have a rigorous proof for the other 3 points? For example, the first one, they kind of say different things, even though both are true.
I believe so. I didn't think too deeply about this.
Okay.
This is one way. I thought about entropies like this a while back, and I found it useful. I got caught into this, and I thought it's an interesting, it's an interesting way to think about that. I don't have formal proofs of this.
So you assume one variable is uniform? You're doing the uniform distribution over one variable? I'm a little confused here. What like how can you just like from the inequality without looking at the database? Can you tell if this is a valid inequality just by looking at the formula?
Can you decide by just looking at one inequality of entropies if that corresponds to a database inequality? And I don't know how to do it. I would have to sit down and try to define a probability distribution for which that entropic inequality is converted into an inequality about the cardinalities. Yeah, so we know how to do this for the AGM bound and the generalized bound, but the lesson is we need to be careful how we use it. We need to be rigorous about this. Yeah, and this is exactly where I want to go. So to recap, entropies are vectors. Once you do the homework, you can forget about this formula. Still remember it. It's good to remember the definition of entropy. We don't need to use it for database applications. And next, I want to show you the things where we stopped last time, how to use entropies to prove more powerful bounds. Okay, good. So generalized upper bound. Why do we care? The AGM bound is very limited. It's really not useful in practice, except for very cyclic queries where the AGM bound tells us something interesting, but otherwise it's too limited. But if we add additional information, additional statistics about the data, we can get very, very interesting and very powerful upper bounds on the query size. Yep, this is the motivation. Quick recap. How do we go rigorously from entropic inequalities to inequalities about databases? Well, we need to be careful how we define the probability distribution. So this is how we derived the inequality for the triangle query. We said, give me any instance D, RD, SD, TD. So this is a concrete instance. And what we are going to do, we are going to consider the output of the query on this instance, which is a table listing all the triangles. This is my output on this concrete database input. And now we are going to define a probability distribution which is uniform. And on this uniform distribution, what we have is that h of xy is not equal to log of r, but it is less than or equal to log of r. And then we apply our entropic inequality, which we know how to derive. And what we get here is h of xyz. And here is where we use in a critical way the fact that we started with a uniform distribution, and this is equal to log of q of d. So the purpose of this slide is to remind you about this connection between statistics and entropic values. We just use the fact that we know the cardinality of R. This gives us a bound on the entropy xy. But we can use more statistics. So one is a cardinality. The conditional entropy is upper bounded by the logarithm of the maximum degree of y for any value x. Okay, and something that we just discovered recently is that you can also have a, if you know some LP norm, like the L2 norm on the degree sequence, you can upper bound some entropic term based on the log of this L2 norm or LP norm. Very interesting. I'll show this to you later. But proving this requires a little bit of thinking. It's not immediately obvious. I'm not going to go over it, but it's not a very difficult exercise. It's an instructive exercise. Unlike this, which should be obvious. Okay, good. So now let's make sure that everybody understands these statistics. Here is a table. And the degree sequence of U is this sequence here, 4 to 1. How did I get here? So look at the values of U. A occurs 4 times, B occurs twice, C occurs once. The corresponding sequence is called the degree sequence of the value U. Okay, the conditional entropy of VW condition on U, no matter what the distribution is, the conditional entropy is always less than log of the maximum of the degree sequence, which is 4. So why is that? Because no matter on what we condition, we don't get more than 4 values here. That conditional entropy is always less than or equal to 4 in the expectation, if we remember the expectation formula. This is why if we know the maximum degree, this gives us a constraint on the conditional entropy. But we can also compute the L2 norm in this case, is the square root of CL2 norm is the sum of the squares of these degrees. And then we get a second constraint, an interesting constraint between a more complicated entropic function. And again, I'm not planning to spend too much time on this, but this is, I find this super exciting. It's also very, very recent. That was if we condition on U and take all the other two variables. We can repeat this, just condition on U and compute the degree sequence of phi condition on U. It's different because if we only consider the output V, then we have a duplicate, and one is a duplicate. So we no longer get four values A, we only get 3 values A because one of them is a duplicate. Yes.
Is there like a reasonable interpretation of this under bag semantics or?
No. If you want to reason about bag semantics, there is a very simple workaround. You add a new attribute, and then you make that distinct for all the distinct values, and this is how you handle bag semantics. Okay, so these are the statistics. Finally, let's see the example that I should have covered last time, but we didn't get there. It's actually a cool example. This is a simple chain query, X, Y, Y, Z, Z, U. It's a full conjunctive query. I should have listed here all the variables, but there was no space. But in addition, we join with 2 huge relations, so huge that we don't want to use them in the AGM bound, but they have an interesting property. They satisfy a functional dependency. Now, without these 2 relations, the AGM bound is n squared, because we need to recover this query by putting 1 on R and on T. Yeah, we need to cover X and T. But now suppose that A and B, this is why they are there. Suppose that they satisfy these functional dependencies. And I think I asked this last time. How many people here do not know what a functional dependency is? Okay, everybody knows. So in A, XE is a key. In B, YU is a key. Interestingly, in that case, the size of the query decreases to n to the power 3/2. And here we can no longer use that query expansion trick because these are no longer simple functional dependencies. So we really need to use entropic inequalities. Yes, Grace?
You only need one of those to get 3 halves, right? Or do you need both?
I don't know how to use only one, but
like if there were no B, if A were there, I think it's still 3 halves.
I would put this probability of 40%. So I don't know, Grace. I've never tried that. I know how to prove it with A and B, and I'll show you. Let me show you with A and B, and you prove me wrong. Yes.
So but if I had if R was like X, Z, Y, then I could expand U into R.
X, Z, yes. Then you can do the query expansion.
So I'm allowed to do the expansion whenever the set of atoms is a subset of another.
Yeah.
Okay, cool.
Yeah, but sometimes you're stuck. There is nothing you can do. Okay, so what I wanted to show you is at the beginning, it's exactly like we did in the triangle query. We start from the statistics that we know, so the log of the cardinalities, and the log of the maximum degree. But what is the maximum degree of U given XE? It's 1, and this log is going to be 0. But I can derive this bound for any maximum degree. And these are greater than these entropic terms. And now we switch hats. We no longer do databases. Now we do entropic inequalities. So how do we prove that this is greater than H of X, Y, Z, U? Well, we apply submodularity, but now it's no longer so simple. We need to choose carefully in which order we apply the submodularity. And I can't tell you how many hours I spent finding the right order, not for this one, but for our complicated ones. It's not easy. So in this case, you start from here, and we apply submodularity. We get H of X, Y, Z plus H of Y. And then what do we do? Actually, I don't know. Let's see what we do. We apply submodularity here, and we get this. So now finally, remember that if we condition on more, we get something smaller. That is also submodularity. So this is what we are going to do next. So I can replace this with condition on x, y, z. And this is good because now what I apply the chain rule. X of h of x, y, z plus h of this is h of everything, x, y, z, u. And similarly for the other two. That's how we get it. So putting everything together, log of this big product is greater than the square of the size of the query, which means that we get this beautiful upper bound on the query size. In particular, if the max degree is 1, then these two factors disappear if we have functional dependencies, as I stated here. And then we get just square root of RST, which is n to the power 3 by 2 if they're equal. Okay, I wanted to show you a second one, just to show you the example. Do you want to go back and, yeah, you're okay? You're okay. I wanted to show you a second one, just to convey to you the excitement I have about these LP norms. Here is the triangle query again. It turns out we can upper bound its size by this bizarre quantity, the product of the L2 norms squared of y given x, of z given y, of x given z, and everything under a cubic root. Yes.
So you always condition the second variable. So for example, like x given c, integral of c is x given c, could you condition the other way? C given x.
You could, but then you need to work out the inequality. It's no longer the same. So I worked it out for this. And how do we prove this? Well, we start from the statistics that we have on these L2 norms. Then we use those connections between the statistics and the entropic terms. And you probably don't remember it, but this is what we need to put here, h of x plus 2h of y given x. And then we do the hard work to find the submodularity inequalities. What I did here is that h of x, I apply the chain rule once, and this takes away one of these twos. We get h of x, y, and we are left with a single conditional. And now we need to find the right submodularity inequalities, and this is how you find them. You apply submodularity inequalities to this, to condition on more, finally the chain rule, and we get this free log Q. Give me just 1 second. Yeah, I want to leave this here while I take Grace's question.
So if I'm just understanding the general structure of this correctly, the problem is sort of twofold. The first is you have to go and figure out which order, what you'd like to condition on in the expression, like in the third degree expressions, and then figure out like the order in which you want to apply these
Submodularity rule.
these submodularity inequalities.
You can think of it this way.
So it's just, but is there like a way, because this is like us, short of just enumerating everything out and just writing it out, right? Is there some sort of certificate to say, okay, I'm good, this is the best I'm going to get with this technique?
Exactly. This is what I'm getting. This is how I like to play. Once I understand this stuff, then I can do these derivations on paper, and to me, it makes me feel good. I know how to prove the inequalities, and they look so beautiful. But a system cannot proceed this way. A system needs to be told which inequalities to use, and we don't know which ones to use. There are actually many inequalities you can derive for the triangle query. As you can condition in the other way, you can use the L3 norm. You just need to work out the inequality. How do we systematically compute this upper bound? Yeah, and this is exactly where I want to go. But let me just summarize what we have seen so far. If you remember, when we started this discussion on the query upper bounds, I told you how current systems work, how database systems do cardinality estimation. For joins, they use the cardinalities of the base tables, and they use the number of distinct values in different columns, which is equivalent to saying that they use the average degrees of those attributes. The upper bounds, we use the same cardinalities. Instead of the average degrees, we use the max degrees. And this is why these upper bounds didn't quite catch up didn't have a major impact in practice, let me put it this way, because essentially they were replacing the average degree with the max degrees. But this is why I'm so excited. Now we know how to also capture these LP norms, which are much finer grain statistics on the data. Even for something as simple as a join, we can derive new inequalities that, I don't think people knew it before, like this one here. Who knew that the size of a join is less than the LP norm of 1 degree times the LQ norm of the other degree on the other side times the domain of y to some bizarre power. Plug this in, it could give you a very good and better bound on the size of the join. Okay, but as Grace pointed out, how do we compute? How do you use these statistics in a uniform way? Yes.
So is there a connection here to the worst case optimal joins? Because when I have like a high LP or is very high in an LP norm, then like a big thing might blow up my norm. So like if I decompose it into heavy and light, is there some connection here?
Nobody knows how to connect the worst case optimal join. This is a big frustration. The worst case optimal join only works in the context of the pure AGM bound. Once you extend it with more statistics, things become complicated, and there is a long story, but no definitive answer. And for degree constraints, it's even worse for LP norms. Good. So now let me get to Grace's question. What is a principled way to use all these statistics and come up with the best upper bound? And in the case of the AGM bound, how did we do it? In the case of the AGM bound, I showed you how to guess those fractional edge covers, but systematically, we used an LP solver. We used a linear program and it's dual. We are going to do the same thing for generalized statistics, but now the linear program is no longer going to be linear in the size of the query. It's going to be exponential in the size of the query. Not good, but at least we know how to compute that bound. Is a bound tight? It turns out that in general, it is not tight, but it is tight for all practical purposes. It really requires very bizarre and contrived queries to make it non-tight. Good. I'm going to talk only about this exponential size program and not get into the discussion of tightness. Okay, so here is how you construct the linear program. You start from your query, and your variables will be these unknown entropies. There will be one distinct variable for each component of your entropic vector. If you have a query with 3 variables, then you need 8 variables in the linear programs. Okay, what are the constraints? Well, for each statistic, you list down the corresponding inequality that statistics imposes on the entropic function. For a cardinality, you write down this constraint. For a max degree constraint, you write down this. For an LP norm, you write down this. And in addition, you write down all the Shannon inequalities, all of them, because you want your program to be able to use all these Shannon inequalities to prove whatever it needs to prove.
And P here is some arbitrary number you choose.
What is P? It's a good point. And this is a long discussion, but I mean, it depends on the engineering. How many do you compute? You have many tables, you have hundreds of tables in your database, each of them with dozens of attributes. How many LP norms can you afford to compute for each of them? And I don't know the answer. This is part of the engineering that would have to be done to incorporate these bounds. But you only write down those that you have. That part is easy. Once you know which ones you have, this is what you write down. This is the system. Let me show you how it looks like, okay? And the goal is to maximize this, the entropy of all the variables. Why to maximize the entropy of all the variables? Because this corresponds to the size of the output of your query. So you want to see how big can my query get? What is the maximum value of the query output if my data satisfies all these input constraints? Yes.
I'm not a really big LP expert, but does this mean that only like two to the end of the constraints are actually useful, like for every program? Because otherwise you'd have like over constrained.
It's not going to be over. I'm not an expert on linear programming either. So that you, in the end, you probably only use some of the Shannon inequalities. If you knew which ones, you can simplify it and only. But I have no idea how to restrict the Shannon inequality. Let me show you how it looks like, because it actually has a very elegant form. Remember? Yes.
Sorry, the P in the previous slide, how do you set P?
Oh,
It seems like a free variable.
this P.
Yeah.
You need to decide when you collect your statistics, for how many P's you collect your statistics. Let's say, just for the purpose of the discussion, that for each table and each attribute, I'm going to compute the L2, L3, and L4 norm, and that's it. Then your P will be 2, 3, and 4, because this is what your database system supports. But don't take this as given. So you might be want to extend to 5. Okay, so let's see the two programs. Remember that I put the fractional edge cover on the left, fractional edge vertex packing on the right. The program that we write now, it corresponds to the fractional vertex packing. We want to maximize H of all the variables. And this is for the triangle query I should mention. We first list all the statistics. H of xy less than log r, pretty clear. H, same for yz, same for xz. If you have more statistics, list them here. All the LP norms, all the degrees that you have, just list them here. Then you move to the Shannon inequalities. This is one. You want to write it less than or equal to be consistent with the rest. Modern LP solvers, they allow you to write inequalities in all directions. But in order to understand them, it's much better to be uniform, to have always less than or equal when you maximize and greater than or equal when you minimize. Is it clear what this says? Just one of the sum modularity inequalities. You write the second one. And you write down all the submodularity inequalities and the monotonicity inequalities. And one way, depending on, you need to be frugal. You want to check which ones are minimal. You need to learn a little bit about this. And I think the minimal ones are actually fewer than 80. It doesn't matter. We just list all the Shannon inequalities. Okay, and this is what you solve. And the solution will give you an upper bound on the query. Why is that? How do we make sure that this corresponds to one of those inequalities that I like to write on with pen and papers? You prove this by looking at the primal. Yeah. So the primal, how do we construct the primal from, or how do we construct the dual from a primal, or the primal from the dual? Every inequality becomes a variable. You see, I already gave them names. These will become the new variables in the primal. The objective function, what we want to minimize, is the sum of all these terms on the right here. So it's going to be C1 log R, C2 log S, C3 log T, and more if you have more statistics. This is the objective function. In addition, we have one constraint for each variable here. There is one constraint for the variable h of xyz. Here is that constraint. And so we read it by adding all the coefficients where h of xyz occurs. It occurs in sigma 1, it occurs in sigma 2. Who knows where else it occurs? You add them up. Question, where does this one come from? Exactly, it comes from here. This is the one. Here we put the coefficients that we had in the objective function at the top. There we have a 1. This was h of xyz. Similarly for the others, h of xy, interestingly, h of xy involves this, this variable that corresponds to a given statistics. But it also occurs with minus sigma 1 because of this. And who knows where else it occurs. H of xy did not occur in the objective. So here we have 0. Okay, and similarly for the others, for h of x, h of y, h of c, and h of c empty set if you want to be pedantic. At optimality, these two are equal. And I claim that what we get from the primal is precisely the best inequality that you can derive with pen and paper. This is what your solver will give you, that best inequality. Yesterday, actually, 2 people in the Simons Institute implemented this because we are desperate to understand some of these inequalities. And the only way to do it is to actually have a solver that gives us a solution because they're hard to find. But I want to make this point that in order to prove that this is indeed an upper bound on your query size, you need to check the following statement. Any feasible solution of the primal consists of these variables, C1, C2, C3, and the sigmas. Any such feasible solution defines a Shannon inequality that corresponds to exactly an inequality that gives us the desired query upper bound. It's a mouthful, and I realize it's not obvious to check this correctness statement. So I put the proof on this slide, but as you will see, I was planning to skip this slide. So I let you double check this at home. But again, the takeaway is it requires some work to make sure that the entropic inequalities that we used previously correspond indeed to the primal dual of these linear programs. Let me know when you're ready to move on. Okay, good. So we skip this. Good. So quick discussion. How are we doing? I should be done in 3-4 minutes. To recap, in the AGM bound, we had a primal and a dual. The primal was there to give us an upper bound. We proved the upper bound using the Scherrer inequalities, but the primal is the one that gives us the fractional edge cover that we use in Scherer's inequality. The dual gives us a fractional vertex cover and the corresponding worst case database instance. How does this extend to the general case? The dual here is kind of more interesting. That gives us a worst case vector, but actually I should start with the primal. The primal still gives us an inequality, but it is a more general inequality that can involve conditionals. The dual, unfortunately, doesn't give us a database instance. It just gives us a vector, H. Previously, from the vertex cover, we constructed the product database. That was kind of an ad hoc construction. Now we are faced with this vector. How do we get a database out of this? And actually, sometimes it's not possible. This does not correspond to any database, and that any database is strictly smaller than what this H gives us. But all things are not lost. There are 2 interesting special cases. One is when this vector is modular, and this is something that you will have to do on the homework. And the second one, when it is so-called normal. I want to show you this case because we are not going to get into the normal ones, but I want to show you in 2 minutes modular functions. And this will, I really hope you will appreciate this slide. So modular functions are still vectors. They are like those entropic vectors, but they are much simpler. They satisfy this condition. For any 2 disjoint sets of variables, h of q plus h of v is h of the union u union v. And they are non-negative. Every modular function satisfies Shannon inequalities. This is something that you need to prove. The homework is trivial, really. It's very, very simple. I want to give an example. Here is a database instance, and it has only 2 variables, x and y, and the probability happens to be uniform. And here is the corresponding entropic vector, 0 as you expect here. Y only has two outcomes, A and B, and A has probability one half, yeah, because it's very uniform. So its entropy is 1. The entropy of X is 2, and the entropy of XY is 3. And the important property that the modular functions have is that H is modular if and only if it is the entropic vector of n independent random variables. Kind of a special, very simple case of entropic vectors. So if our dual program gives us a modular function, they're in very good shape. We can construct exactly a product database. By the way, can you see why this table here, although it's long and unwieldy, it's actually a very simple product database. It's a product of what?
1, 2, 3, 4, and AB.
1, 2, 3, 4, and AB. Yeah, and this generalizes whenever you have a modular function, it's always a product, although the probabilities don't need to be uniform. In our case, we could choose them to be uniform. Okay, so that is my last slide. It turns out, and it's actually a statement that you will need, you will prove as part of the homework. If you start from that complicated linear program, but you only happen to have cardinality constraints, you could have stuck with the AGM bound, but you chose to go to the more complicated program with 2 to the n variables. It turns out, this is a formal statement, that program has an optimal solution that is modular. Since it's modular, it's completely defined by its values at the individual variables. You don't need to consider subsets of variables. And therefore, it could have been computed in polynomial time if you knew that the output is modular. And this explains why the AGM bound is so simple and why the worst case instance is such simple product database. In general, this doesn't happen, but there is a second interesting case, and this is something that we discovered. If all your conditionals are simple, and simple means, I didn't write it here, but it means that we condition on a single variable. So we still have a cardinality constraints, we can still have degree constraints, but on a single variable. We can have any LP norm, but only on the degree sequence of a single variable. Then the dual also has an elegant type of solution, which we call a normal optimal solution, a normal entropic vector, actually a normal polymatroid. We still need to solve a system that is exponential size, but its solution always gives us a worst case instant database. So we are back to a type bound. Okay, I ran over 5 minutes. I apologize for this. That's the end, folks. So next Thursday, on Thursday, we will start a new topic, which are constraints and entropic functions, which will actually strike back. They have an interesting thing to tell us about constraints. Okay, good. I'll stop the video. Oh.